All right, thank you very much for the introduction. Is there a laser pointer up here? This must be it. No? No, a laser pointer. Anyway, so I am here to tell you about fundamental particles, how we're searching for them. And first I'm going to tell you why you should be interested in the search for fundamental particles, why I think it's important. Then I'm going to spend a lot of time describing the nature of the problem, why it's an interesting machine learning problem, and trying to describe it to you in your vocabulary. And at the end, I'm going to ask you to help me solve some of the outstanding problems in this field. And what you're seeing here is the assembly of the detector that we use at CERN. I'll go into that in more detail. But the scale is, it's about 40 feet high, so it's 4 stories. It's a cube of electronics, about 4 stories on a side. And the scale of the assembly is about 2 years in time-lapse photography, condensed to about 15 seconds for your enjoyment. All right. So why are we interested in fundamental particles? Why am I spending my life looking for them? Right? So the answer is that some of these questions here might seem philosophical or esoteric to you, such as, what are the smallest constituents of matter? Where did matter come from? How do things interact? Could the universe have been different? Right? These are the kind of things that college students talk about at 2 a.m. Right? But the interesting things about these questions, among many philosophical questions, is that these are scientific questions that have answers that we can reach, because they're well phrased, and we can actually probe these questions and answer them with particle physics. So some of these fundamental questions that man has been asking about his environment for thousands of years, these are questions that we can answer with particle physics, and I think they deserve answering. Okay, so what do we know? Well, if we try to think about the nature of our environment, if you just go to Google image search and you type in stuff, you get a very wide variety of images, right? So if you're a scientist and you're trying to categorize the nature of your environment, what is everything made out of? You know, you look at this wide variety, you're amazed by the near infinite variety of things in our universe, right? So as a scientist, you say, well, let me group this stuff. I'm going to say, this is plant stuff over here, and this is, objects and food, and you might have some trouble categorizing some things, right? Some things are sort of in the boundary between animate and inanimate. But you can look deeper, and we know we can do better than just botany, right? We can say, we know that every object in our universe, every object that any human being has ever seen, touched, tasted, is constructed of atoms. And take a moment to understand the impressive nature of that simplification. You've gone from a near infinite variety of things we experience in the universe to 100 basic building blocks from which you can construct the entire universe. That's amazing. Infinity to order 100. It's a lots of orders of magnitude, right? All right, but we knew that about 100 years ago. What have we done since? Well, since then we probed inside the atom. We know the atom is made of course, electrons surrounded by a nucleus. And inside the nucleus are protons and neutrons. Right? The protons and neutrons themselves are made up of quarks. So the proton is 2 up quarks and a down quark. The neutron is 2 down quarks and an up quark. Note, I will not answer any questions later about the names of these particles because they make no sense. All right, so if you have up quarks, down quarks, and electrons, you can build protons and neutrons, and you can build atoms, and from that you can build Arnold Schwarzenegger or iPhones or whatever you like, right? So that means that we have summarized the entire diversity of matter in the universe in terms of 3 building blocks. Really astounding, right? So you have to ask, is that it? All right, everything we've seen we can make up of these particles, but are there things we haven't seen? And are there particles that exist that are not necessary to make up these building blocks? Why are there 3 particles? Right? If you were to get the fundamental equation of the universe, the equation of physics that could fit on a t-shirt, the goal of all physicists, would it have the number 3 in it? What does that mean about the number 3? All right, so it turns out there are more particles. And experiments in this century revealed, for example, in beta decay experiments, I won't go into the details, that there are other particles like the neutrino, which is a ghostly particle that hardly ever interacts. And there's a particle just like the electron that's identical in every single way except that it has more mass. Why does the electron seem to have this cousin, this muon? It's identical in every way, but it's heavier. All right, so a few decades more searching filled out this table. There are even more quarks. These is called the charm and the strange. There's 2 neutrinos, so I repeat my comment there. Right? Then the tau neutrino was discovered, and the tau lepton. And you see this table filling out the bottom quark, and then finally, in 1995, there's a 20-year gap between the discovery of the bottom quark and the top quark. This whole table was filled out, right? Now, these, you only need these three particles, the up, the down, and the electron, to build matter as we know it. So why do we have all these other particles? Right? Why do they exist? What do they tell us about the fundamental nature of matter? Well, you see that we've organized our particles in this way, and it should be reminiscent. Right? 100 years ago, when we thought elements were fundamental, we organized them by their properties. Right? We said these guys are very active, and these guys are not active, and these guys are metallic, and you order them by their atomic weight, and patterns emerged. And you were asked, from these patterns, why? Right? And the idea was that these patterns are clues as to a simpler, more fundamental underlying theory, and these patterns were just emergent phenomena from that, right? And we now know, of course, all about electron orbitals, and all of the features of the periodic table come just from the structure of electron orbitals. So, here's the table of the fundamental particles. It has a lot of interesting features in it. Like these particles here, the quarks, there are 6 of them. There are 6 leptons. Why exactly 6 of one and 6 of the other? Our current theory says it's a pure coincidence. The up and the down quark, you combine them to form a proton, which is exactly the opposite electric charge of the electron. Necessary, of course, for making hydrogen or any atom. Our current theory says that's a pure coincidence. I think it's likely that there's a more fundamental theory underlying this, and all the structure we see here is just emergent phenomena of that deeper, more fundamental theory. So in 100 years, or maybe 5 years, we'll have a deeper understanding, and this will seem like old news. Here, for example, you see this is already out of date because the Higgs boson here is dashed because it's yet to be confirmed. All right, so what is going on with the Higgs boson? Maybe you heard something about it this week. In fact, it has popped up in a lot of media outlets. You see the New York Times science section and cartoons about collisions that change the world. And there have even been bombastic quotes from scientists. Like somebody said, "This will have revealed the deepest layer of reality our species has ever probed." Wow, that sounds pretty impressive, right? And I read another one by Lawrence Krauss who said that this was the greatest achievement in the history of human intellect. And I mean, I don't know if it really stands in comparison to the development of language or math or the wheel, but people are pretty excited. So what are they excited about? Well, we might have discovered one more particle, right? And one more particle is interesting because it helps us understand the relationship between all these particles. So what is it that we actually saw at CERN? Well, we ran for a whole year, and we're going to talk about this plot in a lot more detail. But since I mentioned it now, I'll show it to you now. And what we see are this right here. This is what everybody is so excited about. So this is what you expect if you don't see the standard model. It's the red line. Anything above that is possibly due to the Higgs boson. All right, so you're saying, wow, that looks like a fluctuation. And we spent a lot of time analyzing this data and doing careful statistical analysis. How likely is it to be a statistical fluctuation? And the answer is it's about 2 to 3%. Right? So if there is no Higgs boson, you see this kind of thing about 2 to 3% of the time. So that's interesting. It's not conclusive. Nobody's going to win the Nobel Prize next year for the Higgs boson. We're keeping running the machine, and in the next year, the collider will have 5 or 20 times as much data. So we should have much more conclusive statements. But for people who've been looking for this for 20 years, it's exciting to at least have a little blip, right? So these 3 data points are the most impressive achievement in human intellectual history, if you believe Lawrence Krauss. Okay, so I hope I've motivated you that it's an interesting thing to spend your time thinking about what is the nature of our environment and how is it basically built up. Now I'm going to tell you about how we look for new particles and what are the issues in machine learning and analyzing this data. Okay, so how do you understand what everything is made out of, right? You're surrounded by things in your environment. You want to understand what they're built out of. So what do? Well, you take them apart. You can't take Arnold apart, so you turn to your toaster and you say, what is my toaster made out of? Well, it's got screws and bolts and nuts and little bits of machinery. And if you take other items in your kitchen apart, the blender or the oven, you discover it's made of similar things. And you say, oh, wait, the blender and the toaster are not fundamental objects of my kitchen. They're just rearrangements of smaller pieces from which I can build any machine, right? All right, so that's a realization, right? A more fundamental understanding of machinery. That's how you do it in the macroscopic world. Turns out we do it in a similar way in the microscopic world. We take 2 particles, we smash them together with accelerators and look to see what comes out and hope to learn what was inside them. So take this to its ridiculous extreme, right? say you had a toaster collider, right? You asked the government for $11 billion to build a toaster collider, and you smashed them together, and you got a big pile of parts, right? How would you analyze it? Well, you'd say, I got 2 handles, and I got 4 screws, and I got 6 of these, and everything hopefully would be in even numbers, and you'd say, okay, so everything that went in eventually came out, and so I can deduce that there are 2 of these in each one of each toaster and 3 of these and whatever. But a basic assumption you make is that everything that went into the collision comes out of it, right? That assumption is completely untrue when it comes to particles. When you have a particle collision, for example, a proton colliding with an antiproton, these are your beams, they annihilate, and the matter that existed in the initial state is completely gone. All right, so that matter disappears and turns into a new form of matter. It's not rearranged, it's not taken apart and reorganized, it's annihilated, disappears, and reforms. Now you might be thinking, well, this is a big disadvantage because you can't it is made its initial state, right? Well, we're not actually that interested in the initial state. What we're interested in is making weird new final states. And this turns out to be actually the greatest advantage of particle physics, because you can take 2 very light, very, very fast-moving objects and turn them into 2 very heavy, very slowly moving objects. So you don't have to know what kind of particles are out there. Say you didn't know that these things ever existed. All you have to do is smash together light particles, which are abundant, right? Protons are everywhere, at very high speeds, and look to see if any heavy particles are made. Now, if no heavy particles are made, you can conclude that they do not exist. Another amazing thing about our field is negative results can be published, right? And fortunately, since we have a discovery every 2 decades, people like me can still succeed in saying, this particle doesn't exist, this particle doesn't exist, this particle doesn't exist. But this is very important. As long as you pour enough energy into your collision, you can make statements about what particles do or do not exist at that energy level. So if you have enough energy in your collisions, you will see those particles, right? This is why we want to have as much energy as possible. All right, so we don't actually work on a toaster collider, right? We work at CERN. CERN is located at the tip of Lake Geneva here. And it had an accelerator in the 90s, which was lower energy, and then there was accelerators in Chicago, which took over. And they spent a long time building this one. They canceled one in Texas, which would have been even more impressive, but this one is pretty good, and it went online in 2008, but there was a big accident, and it blew up, and we had to take 2 years off to fix it. But now it's back online again. And the collisions happen at the center of a very, very large piece of equipment we call the detector. It's basically a concentric ring of detectors, each of which take a different kind of image of the data. And you can see the scale here. This is the size of a graduate student, right? And they're not actually allowed to walk on the detector because it costs $1 bajillion, right? So what does the detector do? Oh, and so what kind of things might we see? Well, we don't know, right? This is exploration. You turn this thing on, you'll have no idea what's going to pop out. Pink elephants, who knows what, right? And that's the idea. It's exploration. Nobody's ever looked at this energy range before. We've gone up in energy by a factor of 7 compared to the previous accelerator. So the amount of territory that's been opened is enormous. It's virgin territory. It's like if you were an astrobiologist and you got to land simultaneously on 7 new Earth-like planets and look for life. That's a pretty amazing opportunity, right? You're pretty hopeful you might see something new. So we might see things that haven't existed since the origin of the universe because there hasn't been that much energy density since, right? So really unlocking secrets of the birth of the universe. What might happen? Well, you know, some people are worried that there might be danger involved. There was concern that we would turn this thing on and create a black hole which would eat the Earth and therefore the universe. And you know, this cartoon suggests that 13.8 billion years ago, the birth of our universe was caused by the previous universe building a Large Hadron Collider. We now know that's not true. And if you're ever wondering about whether you're in danger, you can always check this website, which is constantly kept up to date. If the Google DNS server reveals this to you, then you know the world has not been destroyed. Okay, so that's how we look for new physics, right? Let me tell you a little bit about how we analyze the data. So we do hypothesis testing, right? This is our statistical tool. We say we're going to compare 2 models. One hypothesis is the standard model, the current thing we know. That's our current description of physics, right? All these particles we've discovered and played with for a long time, versus that model with another particle added, right? That is my dream. My dream is to find a new particle and get to name it after my wife or whatever. But this is the idea, is to discover a new particle. What if there were 4? See, we call this a generation, right? This set of particles. Each of these are identical to the previous, except they're just heavier, right? Charm is heavier than up. Top is heavier than charm. We don't know why. We don't know why there are 3. Maybe there are 4. Maybe there are 7. We have no idea. The goal is maybe we can find more and get a sense for what's going on with this pattern. So how does this work? Well, you collide protons and protons. This is from the Tevatron. At the LHC, we actually collide protons and protons. And the model predicts that if you do this, this new particle will be created. Remember I told you if you have enough energy, you can create this new particle. So we turn it on, we have enough energy. The model that includes this new particle in the menu of particles in the universe says you turn your collider on, this will be produced. Well, how would you know if it were produced? Well, the particles collide in the center of the beam, and stuff comes out, right? The particles don't live very long, things like 10 to the negative 23 seconds, because they're very heavy, they're very unstable. They decay to other particles, particles that are stable, and from the properties of those stable particles, we can deduce that that particle existed momentarily. Now, can we see those stable particles? We can't really see them. You can't take a picture. What we have are concentric rings of detectors, each of which gives us a different piece of information about what happened in the collision. So it's sort of like a digital image. So take one slice. So this, if you have a cylindrical detector, and the view, your view is the view of the proton heading into the center of the detector here. So the collision happens here. Different particles interact with the different pieces of detectors in different ways. So for example, one typical product of the decay is the production of electron. Now this whole piece of the detector is immersed in a magnetic field, and this is a charged particle. So you don't need to know the details, but it leaves a little track here so we can reconstruct its direction. From its curve, because it's in a magnetic field, we can deduce its momentum. A photon, for example, travels right through here without leaving a track. So we can tell the difference between a photon and an electron. Muons have a different signature. I don't have time to go into the details, but I'm happy to talk to you about it individually if you're interested. The thing you need to know is this detector reads out a million features for every single collision. Right? Because we need very high resolution to understand exactly what happened. We're looking at the decay products coming out. We want to know where did they come from, which ones that came from a single particle, this kind of thing. So the raw data is a million collisions. Right? So what does that add up to? Well, we do a lot of collisions. We do 10 to the 8 collisions per second times a million channels. Okay? We can't store or analyze that much data. Fortunately, most of that is not interesting at all. Most of it, the huge majority of it, is just stuff we've seen before and we understand very well. Okay? So we throw all of that away. We call a trigger system that filters that out very effectively. And you can worry about whether there's something in that detector. Is that a question? Yeah. Oh. Well, we don't know because we throw this away. Now, okay, so that's a flip answer. We are fairly confident that most of that it's uninteresting. And when we first turned on, the accelerator ran at a much lower rate, and we kept everything and studied in gory detail and didn't see anything crazy. And we keep a random fraction of this just in case the universe turns on a new particle after we started or something goes crazy. But it's difficult. I mean, it's just too big to understand. So we look for things like production of heavy particles that we know, W bosons, Z bosons, the top quarks. Things we're hoping to see, like the Higgs boson, are produced 0.1 Higgs bosons per second. All right, so it's 10 to the 9 collisions before you make a single Higgs boson. Okay, so it's a lot of data to sift through. And how do we analyze the data? Well, we boil down a million dimensional space, a million features, using our physics knowledge and our intuition and understanding of how things work, into approximately 10 to 50 features that tell you about the direction of the decay products. So instead of just having every single channel's data, you say, well, there was an electron in this direction, there was a photon over here, there was a muon over here. Each of those takes 3 or 4 pieces of information. Maybe you have 10 to 15 things per an event, so it's order 50 things per an event. Now, what we do is we look for some region in feature space where hopefully our 2 hypotheses, remember one of them was the standard model, the other one was standard model plus particle I will name after my wife, right? And we hope to find a space where these 2 diverge, because we're making a scientific prediction and it should be testable. We don't want to make a prediction that is untestable. We want to say, okay, run this experiment, and the data will tell us whether this is the truth or this is the truth. That's the goal. So our goal is to find a feature which discriminates well, which looks different in the two theories, right? Okay, so there are a lot of statistical issues here, right? So say you get the collider data, you turned it on, and the collider says, no, the black line is much more accurate. All right, you can do that intuitively. You can see by eye that particle isn't there. How do you state that confidently? How do you make statistical claims? Well, what we do is we need to understand this probability density, the probability density with respect to our features for both models, right? And then we can just do a likelihood ratio. Say the probability to see this data given the new hypothesis over the probability to see this data given the standard model hypothesis. And then you do confidence limits and interpretations of that.
So how do you make up that red line?
Excellent question. Thank you. So we compare this hypothesis, right? Let me just make one more comment before I get to that. So our ability to understand whether we're seeing this theory depends critically on how different the two theories are, right? So we're looking to maximize the difference in their predictions, okay? And it's important to understand our uncertainty on that prediction, right? If, for example, the prediction is this little blip, but the uncertainty on the black line is this big, well, you're never going to see it because the uncertainty on your background is too big. It's bigger than your signal. So how do we devise these probabilities? Well, here's what we do. We do not have functional analytic descriptions of these probability densities. We just do not, because some of the physics we don't understand, and some of it is because we just don't understand the physics well enough. Okay? So we have numerical simulations of what happens after a particle collision, right? And these are driven by heuristic models. Then, at the second step, we have heuristic models for what happens when particles collide with our detector. Okay? And then we have our raw feature readout, and we reconstruct. We do our boiling down from 1 million features to 50 features. And here, this is boiled down to a single feature. And so this is another example of what you might see for the Higgs boson. This is the falling background spectrum. And if the Higgs boson were there, you might see a little peak here. So you notice that this is kind of jagged. It's because it's a histogram of individual simulated events. We don't know this function. We deduce this function posteriori after running an enormous simulation. Does that answer your question? Now, this simulation is very difficult to use. One second. All right, so we generate, I said this already, we use these histograms to define this. And we've tried things smarter than just histograms. We've tried kernel-based density estimates and smoothing and all sorts of things. But there's no different idea there. It's just you're defining it posteriori, right? You're deducing it after the fact. You have some physics model that you've used to construct this data, but you don't understand it. You can't construct a function in an arbitrary feature, so you have to deduce it after running a bajillion events. All right? So we want to harness all the differences between the hypotheses, right? Maybe there's a difference between the hypotheses, not just in this feature, but in another one. So from that perspective, we want to use as many features as we can. On the other hand, our simulation is painfully slow. It takes 10 minutes to simulate a single collision. So if you need to simulate 1 million collisions, it's a huge amount of time on a large computing cluster. And if you made one mistake in your settings, oh, you got to go back and redo it. It's a huge amount of time. And of course, we have the curse of dimensionality. To characterize the shape in one dimension, you need maybe 100 points. You start going to 5 dimensions, well, 100 to the 5 is a very large number of events. So we want to use as few features as possible. So you see here, we're torn between both of these needs. So we quantify our ability to observe this particle based on how big it would have to be before we could distinguish that theory from the standard model, right? So we'd like to be able to see very small signals. And to be able to see small signals, we need to be able to separate them and have accurate models for both the new theory and the old theory. Okay, so what are we doing, right? We're not just sitting on our hands, we're trying things. So say you have your two theories in some high-dimensional space. I can only plot 2, right? What we do is we separate the two pieces of it, the standard model and this new piece, X. We assume there's no interference. And typically, what we do is treat this as a classification problem. We say there are 2 classes in supervised learning, and we assume that what we actually want to do, which is enhance our discovery sensitivity, is 100% correlated to what supervised learning can do, which is classification. Okay, so you take your neural network or boosted decision tree or whatever, SVM, and you boil this down to one dimension. Right? You try to understand where your signal lies, and you put that close to 1 and the background close to 0. That's what we try to do. Right? And this can be very helpful because it summarizes all the differences in many features into one dimension, which is very useful because we're limited in our understanding in how many dimensions we can use because we have to run this slow simulation and then deduce the shape of the background, so we can't do large dimensions. Right? So having it collapsed into one dimension is very helpful, right? Because then we only have to build a one-dimensional histogram. Also, it's difficult to publish data in a paper in more than 1 or 2 dimensions. Right? How do you publish a 5-dimensional distribution? Electronically, right? But the problem is this technique doesn't account for uncertainties in our predictions. We have significant uncertainties in our backgrounds. If you just feed in your nominal background model into your classifier, you're teaching it to reject that model. But there's uncertainties, right? Your model could be wrong, and we can describe those uncertainties, but we don't ever include those uncertainties into the classification problem. Right? So that's one weakness. Another weakness is that the standard model hypothesis has lots of different categories, right? It's not just one thing that can give you background. There's often 5, 10 different things. It's not always clear how to perform the training in order to account for the varying classes of things and their varying effects on the result. Right? So what we've learned is, with our experience is that it works well when we start with a limited number of features, fewer than 10. If you just say neural networks are God and you just throw 100 dimensions at it that are of raw data, it's not going to be able to figure out where your 2 hypotheses are different very well. Typically, we do a lot of physics intuition to try to understand what features might work well and feed those in the neural network just to collapse us to 1 dimension at the end. So the features have to be very carefully chosen and pre-processed. We've attempted automatic feature selection but never really had much luck with it. And it only really works with fewer than 10 features. So in summary, I'd say supervised learning for particle physics works well when classification accuracy and discovery potential are very well correlated. This isn't always true when you have multiple backgrounds, and it's limited if there are uncertainties in our predictions. And it only works if you've done a good job to choose your features. And the costs of the misclassification are not always the same. So we've tried cost-sensitive classifiers. I mean, we read the literature. Oh, that sounds like it's applicable to our problem. But these problems are not always directly applicable because there's often some technical problem, like it requires you a priori know the cost for the different types. We don't know this, so we can't use it. Or the costs are not necessarily correlated with the labels. It's not like this one has some cost and you discover sensitivity, and that one definitely has another cost. So again, these algorithms, while appealing initially, didn't turn out to be useful at all. In the end, we're not interested in classification. We don't care for an individual collision, whether it was the Higgs boson or was a background. In the end, we want to make a statistical statement about whether the Higgs boson exists in the sample. Right? We're interested in this ratio. The probability of the data coming from the standard model plus X versus the probability of the data coming from the standard model. So in the end, we've had some success treating this just as an optimization problem. Saying, toss out classification, use some genetic algorithm to evolve a neural network which would do better when optimized on your actual criteria. That's had some success, but it's very complicated technically to achieve. All right, so in summary, hypothesis testing is our core statistical problem, right? And I've explained to you how we devise these hypotheses and the limitation of developing the hypothesis in multiple dimensions. I'd say the open issues for us are, how do you handle high-dimensional problems? 5 to 10 features at most can be used, and this is even using a neural network to go from 5 to 10 features down to 1. Another one is how to actually optimize for discovery potential. You know, supervised learning works well in some cases. In other cases, reinforcement learning has been effective. But here's the problem. All of these are black boxes. They do not include at all our knowledge of what's going on. We have some physics knowledge about how these things work. We know how the detector works. We are the ones who wrote the simulation of the detector. So surely we should be able to use our physics knowledge somehow to develop these models more a priori, rather than simply running a simulation blindly and having to interpret it later after the fact to understand what the 2 different models should look like in the features we're interested in. So I have more details of, so if you were to go to IKEA and buy yourself a Hadron Collider, these would be the instructions, and take careful note of the warnings. Always very useful. So I have more details about specific examples of applications we've tried, but I thought I'd see if the time was better spent on questions, if people have them.
So my understanding is that the Higgs boson looks like nothing else. It doesn't look like an electron, it doesn't look like anything else.
That's right.
So why is it so difficult to find out it's so different than anything else?
It's because it's very rare. And its signature, there's nothing else that decays like it, but its signature is not unique. The plot I showed you is production of 2 photons. There's a lot of ways to make two photons. You make 2 photons very often. And the Higgs is very small rate on top of that peak. So that's why it's hard to see, because it just isn't made very often. It's unusual, but rare. It's like looking for a unicorn in a forest, right? You could look for a long time and not see it. Once you've seen it, oh yeah, that's the unicorn, you're pretty sure. But you could look for a decade and not find it.
Isn't that what you said? If you have the suspicion that this was a Higgs boson, you just look at the trace or at something and you say, of course it must be a...
Unfortunately, it's not as unique as a unicorn. I mean, say you have 2 photons, what can you do? You can say, well, I add up their energy. What was the mass of the particle which might have created them? Well, 120 GeV, that sounds like the Higgs boson. But, I mean, look at this data. It's back here. Look at the number of events here in the background, right? You expect, I can't find the button. You expect, this is the Higgs boson. Right? You expect 10-ish events. This per bin is 600 events from background. So there's lots of ways to make these same events, and you can't look at an individual event and say, oh, that was it. Now, 30 years ago, when you were discovering decays of particles, you could have a single event discovery, because you had a picture of the whole event, and you could see these spirals and these decays, and those days are gone. Well, this particle doesn't last long enough. It decays instantaneously to 2 photons.
So I have a question in terms of how the collider works. So what does it make, like if you have the exact 2 same particles that collide at exactly the same speed, the same energy,
Yeah?
it is not deterministic.
It's not deterministic. The same initial conditions twice in a row lead to two different outcomes.
And why is that?
Because God plays dice with the universe, right? Because it's quantum mechanical. So there are physical laws. It's not totally random. There are physical laws that say this will be produced 5% of the time. You'll see this 20% of the time. You'll see this 60% of the time. For an individual collision, a dice is rolled, and you get what you get. You never know for an individual collision. It's not deterministic. It's quantum mechanical. It's always protons. Yeah. It's proton. At the old collider, we collided proton versus antiproton. But it turns out antiprotons are a lot harder to make than protons, for obvious reasons. And, well, I hope obvious reasons. And so this time we just did proton-proton because you can do the same thing.
That might be another factor to take into account, the kinds of particles that you collide?
No, because we are colliding the protons, but the protons themselves aren't the ones that are interacting, because protons are just bags of particles, bags of quarks. There's an up and down quark in there. So what actually interacts are the up and down quarks inside there. And proton versus antiproton doesn't make much of a difference. You can get exactly the same kind of physics.
Is your data available?
Is our data available? Our data is available for collaboration with people in our community, but unfortunately we have a very outdated and unfortunate policy towards the actual data, which can only be handled by physicists in the collaboration. And we aren't pressed by the larger community to make the data public. I don't know why. In astronomy, for example, the public gives you $100 million to launch an experiment, collect data, you get a year to analyze it, and then you have to publish it for other people to do. We're not required to do that. We can analyze it and then throw it in the trash.
So you're showing us this problem, which just looks like you're looking for really simple outliers to a machine learning community, but you can't actually give the data to machine learning.
You and I can work together on it, but you can't do it I can't send you the data and have you do it yourself. Officially. Talk to me afterwards. Thank you. Sure, yeah. Well, you know, there are people who are skeptical of new techniques. There are white-haired physicists who will not accept anything except a picture of an event for a discovery. But the field moves along with or without those people. And if you can demonstrate that you can find the Higgs when other people can't, I'm pretty sure you'll be welcomed. So yes, there are cultural barriers, but there are also people like me who are open to collaboration. So it's not exclusive. No, I did an analysis, for example, where we used genetic algorithms to train a neural network, and I think I had to give 50 talks explaining why it worked. You know, so don't have to do training, or you don't have any labels. Why does that work? And you know, you have to educate the community.
So, don't you have any serious statisticians on board? I mean, you talk about neural networks and these things, and this kind of hypothesis and testing comes out of statistics.
Yeah.
What do these guys have to say to this problem?
Well, I mean, it's not really a statistics problem. We have a lot of statistics problems, and we have a lot of statistics experts who help us solve those problems. But this isn't a statistics problem. This is how do you boil down a large number of features into one dimension. You know, they help us do the hypothesis testing. How do you interpret that? Are you Bayesian? Are you frequentist? What can you say about the universe based on what you saw? That's a different question, right? This is I think, is the machine learning side of it. There definitely are interesting things. Oh, great.
Okay, which is how much more data at the current rate. If you're seeing this small of a bump at the current rate at which you're seeing data,
Yeah.
how many years would you expect to see?
1 year.
1 year.
Yeah, so we ran in 2010, and we got, what's the factor? 30 times less data than we got this year. And so next year we're going to run again and get approximately 30 times as much data as we got this year. The performance is increasing exponentially. So next year we will know whether the Higgs boson is there or not. And we'll probably tell you also.
So would you consider creating like the Higgs boson competition and like giving $1 million to whoever finds the Higgs boson?
If you give me $1 million, I will run that competition.
You got partnered with the X Prize Foundation. They are really looking for these kind of like life-changing problems, and they have the money to fund these kinds of problems.
I will now. Yes, thank you for the idea.
Very successful to launch, people through
Yeah.
space and stuff like that. And I know they are now funding projects more in like natural sciences and medicine.
Thank you for the idea.
Do you think, do you think that you might have found your wife's particle that you haven't reached the right level of energy?
Yeah, I mean, we hoped that when we turned it on, we would discover something crazy instantly, and that didn't happen. So there's two reasons. One is it just could be produced very rarely. So for that, you need to run a lot longer. And also, the machine is only running at half energy because we had that accident in 2008. The soldering wasn't quite good enough, and it blew up. So this time we turned it on only at half energy. So we were running 2012, then we turned it off again, repair it, turn it on again in 2014 at full energy. So then we get to double the amount of space that human species has ever looked at. So that should be
So, the calibration that you're doing to make the model, is to some extent based on essentially calculating to a standard model which fragments you might see and how they work, which is a little bit of a chicken and egg problem. You're basically trying to correct the standard model by using the standard model to figure out what's going to happen.
That's right. I mean, there are things we already know in the standard model. We know that we exist, we know that we exist, we know how it should look. People have been studying for a long time. So we look for it and we use it to calculate our type. But there's the possibility that there could be a new particle interfering with those and changing the way it looks. Yeah. So that's true. We give up the possibility to discover some things by using it as calibration data.
So, how much are you actually occasionally checking that you might have been filtering out some physics that we are simply looking for?
That's very difficult to do. And currently, we're having that with the theoretical community that comes up with ideas for simplifying the laws of physics and saying, we think you should see this kind of thing, or that kind of thing, or the other kind of thing. And so that's not currently in vogue. And so we're looking for it. Now, if we run this thing for 10 years and see nothing new at all, we're going to be going back to the data and considering those ideas. But those are hard and complicated, so we're not trying first.
Right.